Recording's rolling. It's Tuesday, November 18th. We're on lesson 6.2, which is inverse relations and functions. So within inverse relation, one way to get this algebraically is just to swap what's x and what's y and solve for the new y. Right? So you can create an inverse relation like that. And then there's a graphical interpretation, there's a table interpretation. Yeah, some examples here. I'll do some examples with you guys. And then, just like yesterday, you guys know Alex 6-1, 6-2, 6-3 is open. Of course, we're covering 6-2 today. We'll do 6-3 tomorrow. Right. So this is due Friday, and that will lead into Thanksgiving break. So I'll show you guys some stuff about inverse relationships. Actually, a really good example, you're going to skip forward a little bit, is where did the temperature conversion go? Oh, it's right here. Okay. So formula for converting Fahrenheit into Celsius is this expression. But what if you wanted to go the other way and convert Celsius back into Fahrenheit? Well, you could take the expression they give you and just find the inverse, and that would tell you the opposite way to go. Right, so I'm going to rewrite this a little bit as, and this is basically example 4, otherwise, is the temperature in Celsius is equal to 5/9 times the temperature in Fahrenheit minus 32 degrees. So you guys know in the States we use Fahrenheit, so if they say it's 71 degrees outside, well, the implication is that would be in Fahrenheit. Right? But if you travel overseas, maybe they would say the temperature is like 21 degrees.
At 11th and 12th grade, please report to the 4th yard. All 11th and 12th business and APEC students, please report to the courtyard. Thank you.
Okay, so guys, let's say the temperature in Fahrenheit was 71 degrees, and it's plugged into this expression. Okay, that comes out to 21.7 degrees Celsius. Okay? Which, if you grew up in a society that learned to think it's Celsius, that might make more sense to your mind. Okay? But what if you wanted to flip this around? Like, what if you as an American were vacationing somewhere overseas and they report, oh, the temperature outside is about 21.5 degrees Celsius. You're like, okay, well, what does that mean in Fahrenheit? Well, all you have to do is to solve for this Fahrenheit, right? And we'll get a new expression, right? So what I'm going to do is, if I replace this with y and x, it's sort of like I can swap x and y and solve for my new y, right? Which is what I'll do later for another one, right? So multiply those sides by 9/5. So I can say temperature in Fahrenheit, which we're solving for, right? Minus 32 equals 9/5 times the temperature in Celsius. See, all I did was multiply those sides by 9/5. Okay? And then add 32. So the temperature in Fahrenheit is 9/5 temperature in Celsius plus 32. Okay? So now you can go the other way. Okay? Let's see, does that really work? Because with this last expression, I got 21.67 degrees for Celsius. What if I plug that into this? Do I get back to 71 degrees Fahrenheit? Let's see if I do. So 9/5 times 21.67 plus 32 is, yeah, it is 71 degrees Fahrenheit. Okay, so it works both. So these two are called inverse relationship. Right? There's an inverse relationship. Right, how about more generally, like something looks more like a function? Here, what if I do number 8 with you guys? Number 8. Okay. Okay. So we're getting, now it says h of x. I'm just going to change that to y. Okay. So here, I'll start with data. So h of x equals x minus 4/3, or you could say y equals x minus 4/3. Okay. But now for inverse. So I'm going to spell it inverse. Okay. What you can do algebraically is just swap the x and the y. So I can say x equals y minus 4, all divided by 3. And then solve for my new y, and that will represent the inverse relationship. So see, multiply those sides by 3. So 3x equals y minus 4. And then add 4 to both sides. So y equals 3x plus 4.
Here the one to
And that's the inverse relationship. So lots of if I want to, I can write this with this notation. Remember how the original expression was h of x? Well, I can write this as h inverse x. So when you put that -1 superscript, it doesn't mean to the power -1. It's just notation for inverse. And in this case, it's 3x plus 4. So here's your original h of x. And here's h inverse of x right here. You see that? Right. Now, another interpretation of inverse relationships is a graphical interpretation, which just means you swap all the x and y values. Okay. Let me actually take this one. Here, I'll just carry forward for this one and graph both of these and show you guys what this looks like on a graph. So let's get take x-axis, y-axis, and graph each one of these. Okay. Now, guys, isn't this first one the same thing as 1/3 x minus 4/3? It could be that, right? If I just separate that up. Right? So 2, 3. -4/3 could be right out here. Okay. And then if I have a slope of 1/3, like 1/3 is here, then 1/3, right? You continue on like that, right? This would be a straight line. Right? So here's your original h of x function right here. I'll call this h of x. Okay. Now, how about the inverse relationship? Now, I found it algebraically by again swapping x and y and swapping for the new y, and I got this 3x plus 4. So 1, 2, 3, 4 has a y-intercept up here at 4. Okay. And then has a slope of 3, so this would be a point. Okay, and then it just continues on this way. Okay. Okay. So this right here, this line is true. This is h inverse x. It could look like that. Okay. So, all right. So what I wrote down on paper over here. Here's the original function. Here's the inverse function. Okay. And then here's the original function. Here's the inverse function on graphs. You guys see that? Okay. Now watch something funny about these coordinates, because here's one of the coordinates on the original graph. Could this be 4, 0? You guys see that 4, 0? Right. Okay. So what if you swap x and y? Do you get the point 0, 4? And that's exactly one of the points on the inverse graph. 0, 4. Huh. Now, what if that universally works? How about this point right here? This looks like the point 1, -1. Does that look about right? 1, -1. Well, if I swap those, make -1, 1. See, -1, 1. Oh, hey, that's this point right here. Is -1, 1. Huh. Huh. You see, if you just swap x and y. Okay. And this has a y-intercept at 0, -4/3. And this has an x-intercept at -4/3, 0. Yeah. Oh yeah. How did I switch x and y? Okay. So back to the original thing. Okay, so I just pulled number 8 from the book. They gave us this expression. That was h of x. Right? Now h of x I just called y. Right, so we got that. Then all I did was I just swapped x and y right here. So where the y was, I put an x, and where the x was, I put a y. See that? And then I just solve for the new y, and that tells me the inverse function. Yeah, that's it. Now you could go point by point by point, and you could do that too. Okay. And another way to think about this is, if I draw a line y equals x, which I'll just dash off right here, dash off this line y equals x. Okay. This could act as a mirror for the function in its inverse. Is this line right here? Okay. And notice that they also cross each other on that line too. Right. This 45-degree y equals x line. Right. Now there's this funny trick you can do by looking through the paper. So I'm going to break out a marker and make these lines really bold. So here's my x-axis, here's my y-axis. Okay. Here is the original function, h of x. And here's its inverse, h inverse. It could look like that. Okay, that okay so far? Right. Now, what I'm going to do is pick up the paper and hold the corners at the top right and bottom left corner along this 45-degree diagonal. You guys see it? Okay. So hold it right here. Okay. And then I'm going to rotate the paper about this line, which I said could act sort of as a mirror, right? Some kind of symmetry. And look through the paper. Look at that. Guys, it's the same outcome. Can you guys see through the paper, my dark marker lines? Right? Now, what used to be the y-axis is now the x-axis. What used to be the x-axis is now the new y-axis. Right? And this function down here was the inverse, and this was the original, but now they swap places. Yeah. So show it again. Right? So one way to get the inverse, like if you have some crazy graph, some crazy function, right, you want to know what is the inverse, right, and you have no idea, right, you can just draw the graph, and then you can rotate the paper and watch. This graph will show up. Show exactly what its inverse looks like if you look through the paper. Here's that. Good picture. Okay. Right. So, here. I'll do at least one more example with you guys. Right. Here's this number 46. Right. This graph right here. They say find the inverse. Right. Now I did this ahead of time, so save a little time. I'll show you guys what I did. Now one of the points is 2, 2. Right. So Right. So 2 comma 2, that's right there. Okay. And then here, I just repeated that down here. Right. So I just blew this up bigger. Okay. Now, if you reverse the 2 and the 2, well, you still get 2, 2. So the inverse relation would also have that same coordinate. Okay. What about this point, 5, 1? Well, if I reverse those, I get 1, 5. That's that point right there. How about 6, 0? If I reverse that, I get 0, 6. That's that point there. And this point down here is 7, comma, negative 7. So if I reverse that, I get negative 7, comma, positive 7. It's that point right there. Okay. So here's the original function. The original relation is that there. The inverse is this up here. You see that? Okay. And then if I rotate this over my 45-degree line, it looks exactly the same. See that? Look at the paper. Okay. And if you didn't know one of these, like if you didn't know the inverse, but you have the original straight from the book, okay, you could just use rotate the paper trick, and it'll tell you exactly what the inverse looks like. Of course, we did it a couple ways, so it should look the same. Just that. All right, so there's inverse relationships. Here, I'll throw in one more detail before I let you guys go, which is that some of these inverses do not necessarily create functions. Okay, so you might have to modify a little bit if you want the inverse to also be a function. For example, parabolas. Anytime you have a parabola, and I'll do real simple. How about y equals x squared? What if that's your original relationship? Original function. Okay. So 0, 0, 1, 1, 2, 4, 3, 9. Okay. You guys know it's going to end up basically like this, right? Could that be very basic parabola? Okay. Well, if I do the flip the paper trick, let's see, can you guys kind of see through it? Yeah. You see it's going to create the sideways parabola? You guys see that? You see that? Okay. Here. 0, 0, flip that, it's still 0, 0. 1, 1 is still 1, 1. Okay. But everything else is going to create the sideways parabola. Okay. Hey guys, what I just drew in pink, this could be the inverse relationship right here. Is that a function? No, because it fails the vertical line test. Okay. So if you want the inverse to also be a function, what you have to do is some kind of domain or range restriction. I might say, for example, well, maybe I'll only take the top half of this, which originally came from the right half of the original function. Okay. Okay. So if you want your inverse relation to also be a function, another way to say that is the original function has to be 1 to 1. You guys remember 1, 1? It passes both the vertical line test, which all functions do anyway, but also the horizontal line test, which parabolas typically don't. All right. So there you go. You guys got rest of class. You can watch the full video. I'll roll in the background anyway. If you want lots more examples, you can watch it with earbuds. You can work on Alex if you are ready to hop into that.